Work and energy
Hmm.
is like what I'm struggling with because before work and energy, it was the curves. The curves and embankments were very
Oh, gotcha.
hard, but work and energy, I would say, is it was hard for me to understand.
Okay. You
So I
have
would
any
say,
specific problems you'd like some help with? That's usually the easiest way because, I can talk all day long and explain it, but what I've discovered
mm,
is that's not very helpful to students usually. It's only after they tried to work the problems and then they might remember the things I said, like, oh, yeah, okay, that's what he was talking about. So it's perfectly normal, not necessarily a good thing, but it's still perfectly normal for you to sit through a whole lecture and not understand it or anything. You think, I have no idea what he's talking about. It doesn't mean you have a mental disability or anything. It's just the nature of physics and the way our brain works. It's just not ready to grasp things until you get a physical example. So, if you want to pull out any particular problem, I can help you with it, or I can give you just an intro to the version of conservation of energy that I use and sort of explain what all the terms are or whatever.
yeah, can we do that? Can I explain like the terms and like
Okay,
how we visualize work?
no problem. Yeah, let me. So, what I tell my students, for starters, is that basically your work is the ability to make energy or something like that. Energy is the ability to do work. That's another sort of circular version of it. But that's normally what I try to express to my students is what work is. And I try to make a parallel to how it's not unlike the common definition of work. So, for instance, you'd say, if I asked you to mow the lawn and what you knew was the lawn was, let's say, 60 feet wide and 120 feet long, and you're using a 24-inch lawnmower deck, 24-inch lawnmower decks means in principle you could cut a 2 foot wide swath, so that'd be 30 swaths backwards, forwards, until you basically went all the way to 120, then turned around, came back to zero and went back to 120 and came back. That is basically a way of mowing grass. Now, if you think about that and say which one's more
Mm.
work, mowing a 60 by 120 or a 60 by 150, you would probably conclude that the 60 by 150 would be more work than the 60 by 120 because you had to go a further distance. So with that in mind, you realize work is
Mm.
proportional to how far you have to apply a force. The other thing is if you were trying to do that lawn, and let's just say one lawn that's 60 foot by 120 foot wide, if you were doing that with a 24-inch wide lawnmower that weighed, 50 pounds versus a 24-inch lawnmower that weighs 120 pounds, I would suspect you'd find the 120 pound to be more work, and therefore you'd find work is also proportional to the force applied. So what I like to tell my students is because of that, we say work is proportional to force, and work is proportional to distance along which the force is applied. And then the other thing is realize that any component of force that's not parallel to the motion you're trying to achieve is not helpful from a work standpoint. So that's what I'm going to try to go with right now. And explain that to you. So let me go ahead and open up my document so you'll know what I'm talking about here. Duplicate this. As soon as it comes up, I'll share my screen with you. Okay, now I got it. Okay, so I'm going to share my screen real quick, and
Okay.
let me give you that. It should pop up any second. Up, it seems like the Wi-Fi that my, yep, the Wi-Fi my iPad was on is not the same one my computer's on, so I got to switch that real quick. Now I'm ready. And still airplane mode. There we are. Okay, sorry about that taking so long. So to take into account the idea that the force component parallel to the motion is the only one that's relevant, one way of addressing that is work. Here right now, my phone's uh, pin's not connecting. Maybe it is now. Okay. So work is proportional to force, and it's proportional to the distance. That's one way of saying it. But if you want to make sure it's the force parallel to the distance vector, then you can say work equals force dot dl, where, and actually I shouldn't say dl in this case. I'll just say force times the displacement vector. And then that dot product, because it's the dot product, means the first vector's magnitude times the second vector's magnitude times the cosine of the
Mhm.
angle between them. And if you look at a diagram like that, you'll realize that d times the cosine of theta is the component of d that's parallel to f. Or if you look at f times the cosine of theta, that's the component of f parallel to d. So that's the big aspect that you've got to figure out, and then you've got to also allow for the fact that at certain points, if you're walking that lawnmower the 120 feet back or whatever, there might be some parts that has a hill up or something like that, and therefore the forces change as a function of position. To take that into account, we ultimately had to say work is equal to the integral of f dot dl. And the dl is like a differential line segment. So, like, you imagine the curve like y equals x squared is a path you're following. Well,
Yes.
if you took the differential of y, you'd get dy equals 2x dx, because that's what the derivative of x squared is, 2x. So dy equals 2x dx is a little vector that's tangent to the parabola y equals x squared at each point when you substitute the x in. So if you do the DL like that, that allows you to take the path, which might be quite long, and divide it up in little infinitesimal swaths. And because it's divided up in such small swaths, the force is likely to be very constant over that small swath and have a very constant direction. So that's why we end up doing it with an integral. Now, again, work is a way I like to express it is work is anything that can drive a nail. And then I add the caveat that it's important that you have to realize that driving a nail could mean driving a really infinitesimally thin nail, like a hypodermic needle or something, into
Mhm.
really hot butter. So it doesn't have to be a huge force. It doesn't have to be, really brutal thing. It just has to be some force applied over a distance. Now, with that in mind, I made up a different version of conservation of energy. My conservation of energy is U initial plus K initial plus work that you put into the system. So one of the examples I did in class was in class and online was a child sitting at the top of a hill on a sled, and her father gave her a push to get her started. Well, that's putting energy into the system, so you would count that possibly as work in. You might even add
Mhm.
another term that I chose to leave off on the left-hand side, but in this case, I think it's sufficient. And you want to remember that that work in can actually be more than one term. For instance, it could be that the father gave the child a push, and we calculate the work for that. But it could also be that before the father gave her the push, perhaps he had her cocked into a spring type mechanism that when he flipped the switch, the spring would give her a push too. So in that case, you'd have a work term like 1/2 kx squared for the work that the spring did on the girl. Then you'd have an integral of f dot dx term again for the father applying a force to her. Both of those would come under the category of work in. Additionally, the other side, I use potential energy final plus kinetic energy final plus work out. And in the example I did of the girl sliding down the incline, I imagine the workout was at the very end. If she still had speed after going through the rumble strip and the snowy and the frictionful
Mhm.
area, if she ran into a board that was sort of spring compressed, then when she ran into it, her running into that board with cushion so it wouldn't hurt her compresses a spring and brings her to a stop. That work could also be counted as 1/2 kx squared. But you also might want to take into account the loss due to friction when she was riding across a frictionful area of the snow at the bottom of the hill. And for that reason, I called that E loss, because you can look at it as work done against friction and then it just come under the work out term, or you can look at it as, oh, it's stealing some of the mechanical energy of the system by going through this frictionful area. So just like the work in last time, the work out and the E loss can be multiple terms. U, on the other hand, is either normally it's either M G Y and you're allowed to have the y origin anywhere you want. So you're allowed to, for instance, if you're talking about a roller coaster, you don't have to measure the height of the car in the roller coaster from the ground. You could measure it, for instance, from the lowest point on the roller coaster and call that y equals zero. And that's fine too. That's the key thing to understand. Uh,
Mhm.
Two people might not necessarily agree what the zero potential energy is, and that's because you're allowed to add any arbitrary constant to a potential energy and it still won't change. So that's one of the normal potential energies. There's also a version of potential energy, and this one's the only time where one of these quantities is going to be negative. Okay, you might actually figure out some way where you work it out and a quantity comes out negative, but almost always that's going to be as a result of an error. But in one case, there's definitely a case by me writing out this version of conservation of energy in which I have to write in a negative term, and that is the gravitational potential energy that an object has when it's appreciable distance from the center of the Earth. In other words, when your distance from the Earth's surface is comparable to the radius of the Earth, then
Mhm.
you can't use MGY anymore because G changes so much over R. So we end up using that U equals negative GMM over R. But again, that's the only time it's negative. The kinetic energy, on the other hand, I'm sure you remember this, is 1/2 mv squared. But now that we've covered chapter 10 and 11, we know as well, or most of 11, we know as well that kinetic energy can also have a rotational part, and that's 1/2 I omega squared. So when I say K initial on the left or K final on the right, that can also be multiple terms as well. It can be, 1/2 mv squared plus 1/2 I omega squared. And that's even when you're dealing with one object. If you're dealing with conservation of energy of multiple objects, then you're going to have possibly two or five of each of them. In other words, something can rotate about two different axes, so that gets you 1/2 I omega squared about one axis, 1/2 I omega squared about another axis, and then you could add another 1/2 mv sub x squared plus 1/2 mv sub y squared plus 1/2 mv sub z squared. Or you can take all those last three terms and just put them together and call it 1/2 mv squared. So that's what goes in those terms. And the E loss is basically usually a work formula that you use to find the E loss. But sometimes it's something as blatant as if 20% of the energy of this collision went into crumbling up metal and making loud noises, then all you had to do is put in zero point 0.2 times whatever the total energy was before the collision, and that would be how you deal with E loss as opposed to doing a work calculation. Any questions on that part?
Mm,
It's a lot of words, I know. Sorry.
yeah. So the IW, so the K, so the kinetic energy, IW, I is
The moment of inertia.
inertia. Okay, yeah. That's what I thought it was. Okay, yes. Okay.
Inertia, and there's two formulas for that. For instance, moment of inertia can be either the summation from I equals 1 to n of m sub I r sub I squared. That's if it's countable things like a bunch of little let's say a bunch of little balls mounted on a frame of some sort, then you could say, well, this ball is acting like a point particle and its mass is m1 and its distance, a perpendicular distance from the rotation axis is r1. And then here's
Mhm.
another one that's m2 and r2, and you just add all those up. But if it's not discrete like that, it's continuous media, then you can say I is equal to the integral r squared dm, which is some of the calculus stuff that I showed y'all earlier. But yeah, that's where that comes from. And the omega is the angular velocity, but they also call it the angular frequency.
Okay.
And I'll just write this FREQ for short for frequency. And of course, the 1/2 mv squared is mass, and for the m and the v is velocity. But like I said, you could even break it down into x component of velocity squared, and then a y component of velocity squared, and then a z component of velocity squared. Usually, you don't do
Okay.
that, but it's possible.
All right. That's definitely it's helping like on a conceptual level. Yeah,
Gotcha.
it's helping.
So
Yeah.
you can take, just to give you an example, imagine this is a hand throwing up a ball, and we're throwing it up at a velocity of, let's say, 12.0 meters per second is V initial. That ball is going to, of course, go up, reach some max height,
Hmm.
and then fall back down like this, right? So you might want to ask, how high can the ball go if I throw it up at 12 meters per second? So to do that, I take my U sub I plus K sub I plus work in is equal to U sub F plus K sub F plus work out plus E loss. This one, I don't have any weird statements like the father gives the child a push, or you have to go over this frictionful area, or you have to compress this spring, or the spring jettisons this object. No, we're not doing any of that. So automatically, you can immediately say work in, work out, and E loss are all going to be zero. Additionally, since you're allowed to set the potential energy to be zero anywhere you want, it'd be really smart to call the potential energy zero initially. So that
Hmm.
makes that a zero. And then at the top, because we're looking for how high it will go, at the top, in order for it to be literally the top, it must not have any more velocity. Because if it had velocity and the velocity was pointed upward, then it would continue to go higher. If, however, it had velocity and it was pointed downward, then it came from somewhere higher. So neither one of those are acceptable. So we make the conclusion that the final kinetic energy is going to be zero. So now I have 1/2 mv initial squared is equal to mg y final. So you can see that the masses cancel out on each side. That's another
Hmm.
beautiful thing about doing it in symbols, because you can cancel out things that you don't know. Because right then, when I word the problem, you're not really sure if you need the mass to solve it or not. But now you see that it's not, and we get finally that y final is equal to uh, v initial squared over 2g, and that would be 12.0 meters per second squared over 2 times 9.80 meters per second per second. And when we do that calculation, we get 144 divided by 2 times 9.8 in parentheses gives me 7.34 or 35 meters. So that's a way you can apply conservation of energy, just as a short, simple example. Does that make
Okay,
sense?
so yeah, so setting it up with the equation and then you want to substitute in the
The
what you
information that
do
you're
so you can
given.
find out the information so you can find out what you do know.
Exactly.
Okay,
But
yeah, it's definitely easier that way.
yeah, and notice the equations that you come up with are often exactly the equations that you got if you just work this problem kinematically, with the kinematic equations.
Hmm.
But you can't jump to such a problem and say, according to kinematics, this is it. Not if you're working a conservation of energy problem. So if you're dealing with something like the roller coaster problem I was talking about a second ago, you can't use kinematics to figure out what the speed is. If the speed up here at this height was 20 meters per second and it goes down like this and gets down to this height, and you want to know what the speed is there, you can't do that with kinematics because you don't know what's happening on the path between it and all that stuff. So all you can really use is conservation of energy, and it just happens to spit out the same answer you would have gotten if you did it kinematically, but you're not allowed to assume the kinematics would work. Let me show you a slightly different version of just so you get an idea of how we could use some of the work terms. We might, for instance, say a compressed spring has a ball compressed a distance delta x equals 3.00 centimeters, and the spring has a constant of 150 newtons per meter. And we might want to say, well, this ball is going to be launched upward, and then it's going to come back down, and we might want to say y final equals question mark. In other words, the exact same problem, except instead of assuming we knew the initial velocity because a person threw it, in this case, we don't know the initial velocity. All we know is that some work is put into the system by compressing the spring. So let me show you how I'd go about working this one. Again, I would start off with U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. And I don't write this down every time. I'm just doing this to show you how I use it.
Mhm.
I usually, when I go to write down the initial equation, I just go ahead and leave off the work out term and the E loss for this problem because I know neither one of those are going to be relevant. But I'm just trying to show you this is what I'm going through mentally when I do it. I'm going to assume the initial potential energy is zero because, again, we're allowed to say y equals zero anywhere. We just have to realize that that's only going to give us the height from this point right there. So that's okay, but we just have to say y equals zero at that height where the ball has compressed against the spring.
Mhm.
At the top, of course, we know the kinetic energy is going to be zero, and this time the kinetic energy initially is also going to be zero because right now the ball is just sitting in a cocked spring. There's no motion. So what we get is one half. Sorry, I'm writing in red. What we get instead is one half kx squared, where this x is the delta x we just finished talking about, is equal to m times g times y final. Uh, this time we actually have to specify that this mass is 1.00 kilograms. I would have given you that a priori. It's just I wanted to make sure I included it so you'd understand. So now that I have all this, I can plug in the numbers. I'm going to say 1/2 times 150 newtons per meter times 0.0300 meters squared is equal to 1.00 kilograms times 9.80 meters per second squared times y final. So you finally could get y final in this case is equal to zero point 0.5 times zero point 0.5 times 120 times zero point zero 0.03 times zero point zero 0.03. And now I'm going to divide that by the 1 times 9.8. So parentheses 1 times 9.8 close parentheses. And that gives me a very, very small height. And what's worse is one, yeah, it gives me a height that's really not very impressive at all in this case. And I just made these numbers up, so we shouldn't have necessarily expected it to be very physical. Uh, but that would be the final
Mhm.
height. Does that make sense? How we did that?
Yes, everything but the K. So the equation for K, the one, or well, the equation for the work in,
hmm
the
In that
K
case,
x squared,
hmm we
and the
derived that earlier as a potential energy for the spring. We used what's called Hooke's law, and Hooke's
mhm,
law says, and it's not necessarily just about springs, by the way. Hooke's law isn't. It means everything. So what Hooke's law says, if I take this object, this pen, for instance, it's a physical object, and I've got it sitting on a table. If I push down on it with some force, then it's
mhm,
going to shrink by an amount X, and it's going to push back in the opposite direction. So that's why the Hooke's law often has a negative in it. But what it says is if I double that force, then I'll double the amount that it compresses. If I triple that force, I triple the amount it compresses. And that's Hooke's law. But we can't normally examine things like compressing a 2x4 and see how much it stretches because the forces required for such things are huge. And that leads us to a dangerous situation when you're talking with students. So you wouldn't want to do that sort of lab. But if you work out from an energy standpoint, and this is a big thing that you are learning, if you calculate the work done by quote unquote a conservative force and going from point A to point B, Once you calculate that work, if you multiply it by a negative number, you'll get the change in potential energy. And when I did that, that gave us another form of potential energy or work in, and that form is the formula 1 half kx squared, where k is the spring constant uh, for the particular spring that you're using. Again, it doesn't necessarily just apply to springs. It's just springs are
Hmm.
easy for us to see. So there's a K value that exists, for instance, in compressing a 2x4. It's probably the bulk modulus, to be honest with you, but there's a bunch of different moduli you can use in engineering and stuff. So it's one of those. Does that make sense?
Yes, and so for the spring it'll be 0.03.
Yes, that's the compression of it. In other words, if you let the spring just sit there vertically, it's going to reach equilibrium with no mass on it at, let's say, this
Hmm.
height right here. But then when I laid that ball on it, it shrunk 3 centimeters. So it went down. That's the compression from the distance from the equilibrium position of the spring to the position that the spring's currently at. That is the X that you're using in 1 half kx squared.
Okay.
Does that make sense?
Yes, sir. And that all just and so this okay. And so it's easier now because this just flows straight into momentum
Exactly.
because with this you can find out.
Final velocity or final
Hmm.
height, or you can even use it to solve for mass and stuff like that. The big thing is on this conservation of energy equation, the long one I gave you there, uh, we learned 1 half kx squared in the guise of potential energy. So in that case, some people might have interpreted that instead of me saying the potential energy is initially zero, they might have put 1 half kx squared in place of that U initial. And that's perfectly acceptable as well because there's this linkage between potential energy and work done. So one person might work it with UI being 1 half kx squared and work in be zero, whereas another person, like we did, we counted UI to be zero and then work in to be 1 half kx squared. So as long as you count each change in energy it exactly once, then you'll be fine. It doesn't matter where you put it. If you put it in work in or if you put it in potential energy initial, that's fine, as long as you account for it. Additionally, if you have something after the fact, like when the ball comes back up to this max height, instead of actually reaching that max height automatically by running out of speed or steam, if you will, you might put a spring up there and have it compress that spring. You could call that term U final, or you could call that term work out, or you could call that term E loss, but it all would be the same 1 half kx squared.
Okay. All right.
Okay. Yeah, if you've gotten a little behind, don't use that as a reason not to communicate with me. I don't hold things like that against my student. In fact, if
Mhm.
anything, I'd probably give you more credit if I saw that you didn't understand conservation of energy this late in the game, and then by the final exam you've got it figured out. That's like a hero story. That's something where I'm gonna, reward that student for keeping his nose to the grindstone.
Okay. Yeah, I've just got, I don't know. I think I might have to take this again with you. I might have to take this with you again. Uh,
That's okay. I certainly will be glad to have you, but you might not need to. Remember, literally till the final exam is done, you still have a chance to pass. So
mhm.
just do your best. I would say go back and look at those face-to-face tests that we did, and maybe even the online tests. And if you had any question on the face-to-face tests or the online tests that you didn't understand, and I mean understand completely, even if you got the right answer, but you still didn't really understand how it worked, I would say go
Mm.
back and do those problems again. Make sure you know how to do them because that's going to be tested again. In fact, I literally look in face-to-face test one, and then I'll look in face-to-face test two, and see what a good fraction of my students might have missed, and I'll put that in face-to-face test three, and probably even put it in the final.
Okay.
And it's not like I'm not doing it to be mean. I'm doing it to make sure you guys don't miss any aspect of the course. So I want to
Mhm.
make sure y'all can learn all of it. There's almost nothing that we'd call fluff in physics. There's no single topic that we can say, oh, you'll never need this, so just don't worry about it. No, we can't do that because physics feeds into engineering, and engineering is very, very broad, and physics, of course, is also very, very broad. So I have no idea what your life may entail, and it might be that you ultimately end up in some track where that one little thing I said was optional was not optional. So that's
Yeah.
what we're trying to do.
Okay. All right.
You find any specific problems or anything you want help with, or is this just a good help to get you started?
This is just a great help to get me started. Because I
Okay.
was looking at videos for this and I was just still struggling. So I was like, I'm gonna just go in on Thursday and ask.
Yeah, and Mondays and Wednesday, I'm on campus, and I usually try to get there at 7 a.m. I tell my students I'm going to be there at 8 a.m., but I also tell them to, send me an email if you're planning on coming, because sometimes, I'm a father, I'm a husband, and I'm helping raise my nephew, and my mother-in-law lives with me. So sometimes things come up and I have to miss. But if
Mhm.
you had set up a appointment with me to show up at that time, I would send you an email and let you know, hey, I can't make it this time. So it's better to do that. But I'm always supposed to be there by 8 a.m. and class doesn't start till 9:30. So
Okay.
yeah.
I will keep that in mind on Monday because I get to campus on Mondays and Wednesdays at 2, but I can definitely come
Oh
a
well,
little
I'm
earlier.
there. My last class starts at 2. So you could come later as well if you wanted. And in fact, my first class on Mondays and Wednesdays normally runs from 9:30 to 12:20. Uh,
Hmm.
but we're in the last weeks now, so I'm letting my students take some extra time to work on practice for finals and stuff like that. So I'm not starting my lab till 10:30. So you still have right at that end, just before your 2 o'clock, you could show up at the lab time. The lecture time I can't offer you any time in there because obviously I have to lecture, but that runs from 12:30 to 1:50, and then my next one starts from 2 and ends at 3:20. But you can certainly catch me at those times.
Okay. I definitely will. And I just talked to Professor Dale, and she
Hmm.
says very great things about you.
Yeah, she's an awesome student-centered teacher, man. She's a
Yeah.
good friend too, so that's
I
awesome.
just finished her differential equations class.
Oh yeah,
Yes,
you make
sir.
an A. You
I
don't have
did
to
get an
sell
A
out
in
for
that
us.
one.
Good job.
This yeah, math was pretty calculus is pretty okay, but the physics it's just such a new concept that it's just
Yeah, and it's got this way of finding the one little thing that you didn't understand in pre-calc, or the one little thing you didn't understand in pre-algebra, or the one little thing you didn't understand in calc one, and dang if it doesn't exploit that every time. That's just the way physics does it.
yes.
I remember I'd because I was a really what we call a late bloomer. I was a deadbeat, horrible student up until literally like my senior year of high school. I was just a loser, uh, just because I wasn't interested, really, to be honest with you.
Mhm.
But it turned out that ultimately, uh, because of all those years of being a bad student in high school and all that stuff, every day I ran into something that I should have known already because we taught it in high school. Simple geometry stuff like if you want to find the center of a circle, you can inscribe a right triangle inside of it, and then the center of the hypotenuse will be the center of the circle. So little stuff like that they expect you to know in physics, and I didn't know that. I'd never learned that, but luckily I was able to find it on the internet. So you slowly have to build yourself up to learn these things.
Oh yes. Oh yeah. Okay. All right. And then yeah, I gotta do the lab for today.
Yeah, the
Right.
lab that we did last week is supposed to be due by, I think I had set it up at 11:59 p.m. tonight to get it done.
Mhm.
But that being said, I'm a little behind on my grading, and you also have a little bit of a safety factor because I grade in the order that y'all turn them in, and I'm like on number lab. Actually, I'd finished 6. I haven't posted the grades, so I think I'm on lab 7 now. Uh, but if you're, not at a lab, if I'm not grading lab 9, then you're fine. If I'm not grading lab 10, then you're fine not turning in 9 or 10. So just get it in as quickly as you can, and if you need a little extension, it's probably going to work out fine.
Mhm.
I wouldn't do it later than 1 or 2 extra days, but at 1 or 2 extra days, you're probably not going to even get a penalty for being late.
Yeah, because my lab, I think that's what's gonna kill me is my lab grade. I would, because I usually work on Thursdays and I work
Hmm.
long hours, and so then I'll get home and I'll be tired. I'll fall asleep, and then I'll wake up the next day. I was like, oh, the lab was due yesterday, so I just haven't. So I just missed a
Well,
few
you're lucky. I
labs.
partly on purpose initially, I held off grading because I was trying to get students into the hang of what you're experiencing now of doing one, a lab on your own, and then two, being disciplined enough to turn it in on time and remember. So I was giving a lot of leeway, and I ended up I don't know. It's a sort of a punishment for the students that are doing it on time, but I don't mean it that way. I'm just trying to make sure everybody has a chance to pass
Mm.
and do well for that matter. I don't want you guys just passing with a D, because then you're gonna have to take it again if you transfer anywhere. And I don't really want you passing with a C. I want you to master it. So I hope you can all get at least a B, if not an
Yeah,
A.
that's what I'm trying. I'm trying to at least get like of course, you get a C, you can go to the next. And I'm trying to at least get a C, but I am doing a lot of work. Like I found a ChatGPT physics model,
No, there you go.
and it's basically going through the whole. I told it what textbook, I gave it the ISBN number,
Oh
and
wow,
it's going through the textbook chapter by chapter with me, and
that's cool.
it's example and spitting example questions and going through the concepts and stuff. So I've been doing that because I need to I want and need to understand it.
Yeah, what's your
It's
major?
just engineering.
It is a branch of
So
engineering.
yes, I want to go into computer.
Okay. I actually did a little bit of software engineering myself. That was my first job out of my PhD program. Was I was hired as an electrical engineer because we were
Mm,
writing code to help electrical and computer engineers create, hard drives and CPUs and stuff like that. I worked at a company called
mm,
Avanti, and we wrote software to design integrated circuits. So in that case, I was a computer engineer because we were writing code, but I was also an electrical engineer because we were writing code about stuff that had to be done regarding CMOS and all that other electronic venue stuff. So it's a good field, but like I said, engineering is based on physics, and physics has got a way of finding any little weakness that you have and saying, "Oh, you're going to have to come up with this today. Today we're going to learn quaternions or spinors or something weird like that."
yes, so definitely. Physics is my weak point because been coding my whole life and things of that sort, and I've
Oh,
seen
cool.
circuit boards and stuff, and I've built PCs. So
Oh,
it's
there you go.
really just I'm putting all my energy right now into physics
Yeah.
because I was taking this differential equations, and I'm also taking the intro to programming course, which is going well. So
It'll pay off. Don't worry. The Manhattan Project, for instance. I don't know if you saw any of the Oppenheimer movie or any of that kind of stuff or read any of those biographies, but 99.9% of all the work done in the Manhattan Project wasn't really physics. In fact, the Robert Serber was Oppenheimer's assistant, and Robert Serber was just a grad student at the time, and he gave the introductory lecture to the physics of a nuclear bomb in like a 30-minute little interval, and it's been released. You can read it yourself, and the physics of it was completely worked out. But what did they hire? They hired a bunch of physicists, and the physicists did the engineering. And it's not in any way that I'm saying physicists are better than engineers. Nothing like that. In fact, that made it harder on the physicists. But if you understand the physics, engineering is just applications of physics.
mm,
So
mm.
the more you put into physics, it's going to pay dividends to you.
I feel like this is just like math because calculus one. When I took that, I struggled in it, but calculus two, the was built on calculus one. Calculus two was very smooth. I got an A in calculus two. I got a C in calc one. It was hard because it was a
Right.
new concept, and then calc two I got an A, and then differential equation I got an A. So I
There you
feel
go.
like it'll be the same with physics, where as it builds on itself and we use the repetition, it'll get
Yes.
better.
Yeah, it'll get better and things look more familiar. And it's weird, but once you finish the like 2 or 3 semester sequence, depending on what you take, there is a third sequence of this that a lot of universities require you to take, and that's just nothing but modern physics. But when you do take that class, you're going to learn a lot of stuff that'll come in handy in various branches of engineering, and it'll definitely pay off. And
Yes, sir. All right. Well, thank you for taking the time with me this morning.
no problem. You have a good one, Chris. And I haven't decided yet. I was actually going to do a one lab, but I changed my mind at the last minute. So I'll be posting something about that. You might not even have another lab to do this week. That's what I'm trying to hint at. So hopefully I'll figure out something that works out really well and can give you guys the time you need to do your work on other stuff. And I might do that in lieu of lab this week. So have a good
All
one
right.
and text me or email me if you have any questions.
All right. Yes, sir. Thank you.
You're welcome. Have a good day.
You as well. Bye-bye.
All right. So glad I was able to help him. I'm going to go ahead and kill this and think some more about what I'm going to do with lab, and I'll be posting something on my YouTube channel later. I'm definitely going to post this just because I think it would help anybody else. One, to know that other students right now are still having problems with what we covered in chapter 8, for instance, 7 and 8. I think it helps you to know that that is not good. We don't want you to be behind, but it's not a panic situation. You still have a good chance of being able to pull off an A in the course. So hopefully that intro that I gave him might help you a little bit and solidify some concepts. So have a good day, everyone. Bye bye.